Let's review our activity. Based on the muddiest points, I saw that there were some issues with the span, visualizing the span, relating the span with the equation ax equals b, and describing when the equation ax equals b has one solution, infinitely many solutions, or no solution. First, let's review the span. A span of one or more vectors is a linear combination of the set of vectors. That's to say that if y is in the span of the vectors v1 through vn, then we can find constants x1 through xn such that y is going to equal to the linear combination of those vectors. x1 through xn are sometimes called the weights of v1 through vn. So I'm trying to make it clear that x1 through xn are constants, are scalars, and the v1 through vn are vectors, and y is also a vector. Let's take a look at a graph of a vector. This is a vector in 2 dimensions. The vector 2, 1 can be represented as a 2 by 1 matrix, a column matrix, and we have 2, negative 1 looking like a point, and a vector can be represented as a directed line segment that starts from the origin to that point 2, negative 1. Now technically the vectors can move around because the vectors have direction and magnitude, and it doesn't say that they need to be in this spot at the origin, but for simplicity's sake, let's take a look at our vector as a line segment, directed line segment. Now if we only had one vector, we can scale that vector, and then that would represent the span. So let me create another vector called w1, and let's say that w1 is equal to x sub 1 times v sub 1, and we'll create a slider for x sub 1 over here, and let's change the color of this to make it look like it's kind of reddish, and let's make a dotted line out of this. So what we can do is we can stretch this going left or right. So the scaling, according to my scalar here, goes from -5 to 5, but technically it can go on forever. Now if we find all the linear combinations, I think we can do that by leaving a trace and have this move around. We can see that the image that this will leave is a line passing through the origin and the point 2, negative 1. So I think it's safe to say that the span of one vector is a line passing through the origin and that runs along that vector. Okay, so let's stop this now. And let's take away the trace, and let's get this back to, I don't know, somewhere between 0 and 1. So now let's find another vector. Let's create another vector. Let's say v sub 2, and let's say that that's going to be the vector from the origin to, let's try 1, 1. So now we have this vector going from 0, 0 to 1, 1. And let's do the same thing. Let's scale this. Let's call it W2. And let's scale this by x sub 2. And we'll create a slider. And we'll change the color, make it orange. We'll make it dotted as well. And if we show the trace and have this run, we can see that one vector again creates a line passing through 0, 0, and wherever that goes. So that's still talking about the span of one vector. So if we have the span of one vector and we have the span of another vector, then they each span a line. Now that's not yet taking into consideration the idea that we can have a linear combination of these two things. So let's do that. Let's get rid of this. Where are we now? I think that we need to find W2. Let's put W2 over here. Let's keep this from tracing again. And so now let's add W1 and W2. So W1 plus W2. And then let's make this green. And let's keep this solid. So the sum, remember, is going to make a parallelogram. I don't care too much about the parallelogram. What I care about is where this green vector goes. And if we let the slider run from -5 to 5 for x1 and -5 to 5 for x2, then we can kind of see that we can capture anything we want. Actually, a good visual for this is that if we have it show the trace. And then let's just let this run. We can see that this vector, the linear combination of those vectors, looks like it'll span anything on this xy plane. Now it looks like it's getting cut short here, but technically we can have any number we want. And regardless of where we are in the xy plane, we can always get to that number or that point or that vector by just finding a linear combination of these things. All right. So maybe that's enough of that. Let's stop this animation. Let's keep this from doing the trace now. And so this thing looks like it spans all of the XY plane. So that means if I pick a point, any point on the XY plane, let's say -1, let's see, the point -1, comma 4. Then that means I can adjust my slider here to be able to reach that point with an appropriate value for the slider. So kind of doing this graphically is not very easy because we're trying to pinpoint. I think that might be good. So about x value of x1 value of -1.7 and a y value of -2.4 or +2.4. Let's try that again. An x1 value of 1.7 or an x2 value of 2.4 will get me to that point. So if you write this point, or we can take a look at this as a vector. If we write this vector -1, 4 or -1, 4, you can write that as a linear combination of v1 and v2, and that's 2, -1, and 1, 1, and find those weights. So remember the equation, if we only have two of these vectors, then we're only looking at y is equal to x1 v1 plus x2 v2. And so with those given v1 and v2 and the point that we were looking for, we can find the value for x1 and x2. And the value for x1 and x2 looks like it's probably going to be negative 1.7 for x1 and 2.4 for x2. Okay? All right. Now let's take a look at what happens in 3 dimensions. So this is GeoGebra again. There's 3D graphing. And I have a couple of vectors here. I'm calling v1 and v2. So the vector v1 is 1, 0, negative 2. The vector v2 is negative 3, 1, 8. So these are my vectors. And then if we do the same thing, where we said w1 is going to be equal to x1 times v1, and we'll create a slider for x1, we see that we can stretch that out. Actually, we can change the color here to red again. We can stretch that out and it can keep going on forever. Oops, I'm losing control over this. Here we go. Okay, so if we temporarily take that out, the other vector, and just focus on vector v1, the span of v1 would just be a line again. A line going through 0, 0, and that point 1, 0, negative 2. Now, if we incorporate our v2 and then have another span of that, so let's call it w2 equals x2 times v2, and we'll create a slider for x2. Then we'll change this color also. Then the span of that is also going to be a line. All right. So the span of one vector is a line. That's basically it. Now what happens when we take the linear combination of these two things and take the span of 2 vectors? Let's put this away for now so that we're not confusing ourselves, and let's just look at the linear combination of those 2 vectors. Let's change the color to green again. And let's see if we can have a trace, show the trace. And let's let this run back and forth. So this is harder to see because it's happening in 3 dimensions. Not only that, but the points themselves are not very nice. Or the vectors themselves are not very nice points to deal with. But it looks like, well, I don't know how it looks like yet. Let's change the speed of one of them. I'm going to change the speed of x1, so we might be able to see more of a trace. So if you're looking at this from a certain angle, it looks a little messy, but if we look at it at just the right angle, it looks like it's staying within a line. But that line from that angle, if we change the angle, it looks like it's more of a plane. So in fact, what's happening here is that the span of 2 vectors is going to generate a plane. In 2 dimensions, we saw that we were able to generate the whole span of things. Because the 2 dimensions is exactly the plane. It's the XY plane. In 3 dimensions, trying to picture the plane is a little bit different. But if we have 2 vectors and we find any possible linear combination of those two vectors, it looks like we will actually get a plane. So let's pause this for a minute, and let's take a look at the plane. What's that plane going to be? I think we can create a plane by doing a surface command. So our surface command will involve those vectors. I think the parameters that we can use are u and v. So u times v1 plus v times v2. And then I think we have to include the limits for u. So u goes from, let's go from -5 to 5, and then v goes from -5 to 5. And we'll change this to make it run a little bit better. But here is the plane that we're looking at. It's just going from -5 to 5, but we can expand this to go from -10 to 10, just so we can see a bigger plane. So here is the plane, and those two vectors are on the plane. Let's get rid of this other spanning vector that we had. So here we go. We have a surface, we have a plane that has those two vectors. Okay, so the span of two vectors is going to be a plane. If the vectors are in 2 dimensions, then the span of those two vectors is the whole 2-dimensional plane. If those vectors are in 3 dimensions, then the span is going to be a plane in 3 dimensions. You can probably guess that if you have 3 vectors, the span of 3 vectors in 3 dimensions is going to be all of the whole 3-dimensional space. And this carries over to higher dimensions, so 4th, 5th, and 6th dimensions. Conceptually, we can imagine that, but we cannot visualize it because we can only visualize up to 3 dimensions. All right, let's take a look at the problems now that we were dealing with. Here's our first problem. We have these two vectors, and we have y is equal to this. And they say for what value or values of h is going to make y be on the plane spanned by v1 and v2. Well, that example that we had already uses v1 and v2. So v1 is 1, 0, -2, and v2 is -3, 1, 8. So let's throw in our y vector, and y is equal to the vector, and let's throw in that parameter that they had, h. And the other two numbers are -5 and -3. And we need a slider out of this, so we'll create a slider for h. So this is our vector. Let's make our vector purple here. I don't know, it didn't turn purple. Purple. So the question is, for what value of h is this vector going to be on the plane? So if we take a look at it from many different angles, we can move the h value until somehow it gets to be on that plane. So I think we went a little bit over. Let's take a look at it from this angle here. And move h a little bit more, and it looks like right around there h is going to be on the plane. There we go. So negative 3.6, maybe negative 3.5. If you did that problem correctly in our in your worksheet, we got 7/2, I think. And so that was the value that we were looking for. Actually, negative 7/2. So when h is equal to negative 7/2, we get to have y as a linear combination of y is going to be a linear combination of v1 and v2. We can actually find out that linear combination. I think this is the vector that we have. Let's change the color from green to blue, maybe. And we can adjust. Oops, I think it's still tracing, so let's see if we can undo the trace. And we can adjust this somehow. To make it match that purple vector. Okay, this is all happening on the plane, by the way, if you didn't notice. And so here, it looks like we need to extend it more. Well, maybe the values would go beyond negative 5 and 5. So maybe you can find the weights so that this vector, the blue vector, is going to be on the purple vector. But in terms of answering the question, it looks like the value of h can be equal to negative 7/2 or negative 3.5. So if you find this equation, set this up and solve for x1 and x2, then we can have that linear combination. In fact, why don't we do that? And this is going to lead us to our next objective, and that is to write this as ax is equal to b. So let's take this side first. This can actually be written as a matrix. So let's get our matrix going. It'll end up being let's try that again. It should end up being a 3x2 matrix, where the first column is essentially the first vector. That's 1, 0, minus 2. And then the second column is the second vector. And then what we have is x1 and x2. So this matrix and x1, x2 combination is equivalent to this if we do the matrix multiplication. Now, if this thing is supposed to equal to the y vector, then we have this equation. So this is our matrix vector equation. A is the matrix 1, negative 3, 0, 1, negative 2, 3. X is the vector that has x1 and x2. And we want to make it a vector. And then this is your y vector. Now we can put y here, but sometimes we kind of know it more as b. So ax equals b if we change this into b. And then if we solve for this, we can rewrite this matrix as an augmented matrix and just solve for that. So let's do that. 3x3, or we have 1, 0, minus 2, minus 3, 1, 8, and negative 3.5, negative 5, negative 3. So if we row reduce this, let's do the row reduction where we're going to take the first row, multiply it by 2, and then add it to the second row, and then replace the second row. Then we would have 2 times 1 is positive 2, plus negative 2 is 0. Negative 3 times 2 is negative 6. Negative 6 plus 8 is positive 2. And negative 3.5 times 2 is going to be negative 7. Negative 7 negative 7 minus 3 is negative 10. And so we do one more step here where we take our first row, or second row, sorry, and multiply the second row by negative 2, and then add it to the third row and replace our third row by that. So when we do that step here, we're going to get this to be negative 2 times 1 is negative 2, negative 2 plus 2 is 0, negative 2 times 5, negative 5 is positive 10, positive 10, positive 10 plus negative 10 is 0. So now we have our solutions, where we can find our solutions. By that last, or by the second line over here, we can see that x sub 2 is going to equal a negative 5. And then we have 1 times x sub 1. So x sub 1 minus 3, oops, let's make this into an equation. X sub 1 minus 3 times x sub 2 is equal to negative 3.5. What does that mean? Especially when we know the value of x sub 2. X sub 2 is equal to negative 5. So x sub 1 is going to equal to, this is going to be positive 15. Added to this is going to be negative 18.5. So minus 18.5. So if x sub 1 is negative 18.5 and x sub 2 is going to be negative 5, then we can have the value match up. Let's go back to our graph. So remember our vectors, our v1 and v2 vectors are given here. And then, so let's see if we could just write a linear combination of v1 and v2. So v1 plus v2 would be this vector in blue over here. Let's make this vector in red so we can see it a little bit better. So this is the vector that we're looking at. This is the vector, remember, that where we made the h equal to negative 3.5 that made us land on the plane. And so now let's just multiply this by, what is it, negative 18.5 times v1, and then over here we're going to get negative 5 times v2. So if we see that, I think we get that overlap between those two vectors, so we can say that they're essentially the same vector. I think the h is 3.5, so if we really make it 3.5. Let's make it 3.5, and then they would exactly be the same vector. Okay, so that's a little bit of the work that's involved with that particular problem. All right. Let's shift gears now and take a look at problem number 5, where we have an A matrix and a B matrix, and they want to know about this equation AX equals B. And let's see if we can relate this to the span. Now, if we kind of work backwards and describe what this equation means, this equation can be written as ax is equal to b by writing this matrix times the x vector. So that's x1 and x2 is equal to the b matrix, b1 and b2. What does that mean? That means we could take this this first vector, the column 2, -6. So we can actually take that column vector. Let's see how to write. Let's see if we can rewrite this properly. So we're going to have a column vector of 2, -6. And then multiply that by x1 plus. And then we're going to have another column vector multiplied by x2. So the column vector for the second one is -1 and +3. Multiply this by x2. And so this is going to supposed to equal to the b vector. So what we have here is we want to know what the linear combination of these two vectors are if we take a look at the column vectors. So 2, -6, -1, +3. Let's take a look at our graph. Let's see. We want 2, -6 and -1, 3 as our v1 and v2 vectors. So 2, let's change this to 6, -6, and then let's change our second vector to be -1. See if we can get it fixed. -1, 3. Now let's take everything else out because it might get a little confusing. But if we take a look at these two vectors, they look like they lie on the same line, right? Let's change this first vector, v1. That's v1. Let's make this a green vector. Let's make v2 a blue vector. So we have these two vectors. Now if we take the span of them, I think if we remember we multiplied v1 by scalar x1. If we take the span of that, oops, let's have it drawn here. Oh, we don't want that. We want this drawn out. Okay, here we go. If we take the span of that, it's going to be a line. And if we take the span of the other one, that's also going to be a line. Now if you take the linear combination of both of them, we'll see that it's actually, they're all on the same line. And so with this information, it does not look like we can get anything outside of that line. I don't know if that makes sense, but you're kind of restricting your outputs to be just that line. So let's take a look at what happens in our work here that we would do. If we were to go back to this equation, we can make an augmented matrix out of this. I think the augmented matrix happens when we add another column here. And then put B1 and B2. And then we'll do one operation. I think that's all we need. one operation here where we're going to multiply the first row by, looks like we multiply this by 3 and add it to the second row. And then we're going to replace the second row. So let's see what happens here. This is going to be 0. We're going to multiply this by 3. We're going to get negative 3. Negative 3 plus 3 is 0. And then we're going to multiply this by 3 and then add it. So this is going to be 3b1 plus b2. So if this is equal to 0, then we're going to get a solution. In fact, we're going to get an infinite number solution. But if this is not equal to 0, then we have no solutions, because we're going to have 0 on the left-hand side is equal to something non-zero. So we have solutions if this expression is equal to 0. And if it's not equal to 0, then we have no solution. So b1 plus b2 is equal to 0. What is that? Well, let's go back to our graph. b1 plus b2 is equal to 0. Well, b1 plus b2 is equal to 0 doesn't really make much sense. But let's let x equal to b1. Actually, let's say it here in our equation. 3 times x plus y is equal to 0. Let's graph that and see. 3x plus y is equal to 0. So 3x plus y equals 0. Can't see it. Well, you can't see it because it is exactly this line. So let's clear everything else out. So here we have it. That line that's spanned by the two vectors. Vector 1 is 2, negative 6. Vector 2 is negative 1, 3. That line is 3x plus y is equal to 0. That line is essentially this thing. So let's see if we can answer the question. Show that the equation does not have a solution for all possible b. So what they're saying there is that if I take a b, that's some random point, so let's say 0.11, then I'm not going to have a solution for that. Okay? So any random point that I pick, the only point describe the set of b for which ax does have a solution. If I pick a point that's going to be on this line, then I would be able to satisfy my vector, my solution. So if I pick any point, like let's say when x is equal to 1, y is equal to negative 3. So 1, negative 3. So if I pick my point instead of 1, 1 to be 1, negative 3, then I'm going to be on that line. And then those vectors, the v1 and v2 vector, v1 and v2, I can find a linear combination of those two vectors to land on that point. Okay? So that's a lot of information, but I hope that walks you through the idea of a span. It gives a good visual of the span. It gives a relationship between the span and the equation, and it tells you about the equation, whether it has a solution or not. So when you have zeros on the left-hand side of the augmented matrix, one of the rows full of zeros, and then the right-hand side of the augmented matrix is non-zero, then you have no solutions. And if you have a row full of zeros, then you have an infinite number of solutions, like in this case. All right, so I hope that helps.